All right, so we're going to demonstrate the definition of an ellipse and how we can use that definition to actually create an ellipse. So I have here a piece of string of a set length, right? So it's constant. And I have I have a grid laid out, and I have some nails at various points on the grid on the x-axis. So I have two nails in each 3 away from the origin. Then I have another 2 that are 6 units away, and then another pair that are about 7.5 units away from the origin. And so the ellipse, remember, is a set of points such that the distance from the point to one focus plus the distance from that point to the other focus is constant. The sum of those distances is constant. And so that constant distance is going to be our string. So let's try these first. So I have 2 foci in this case, both at -6 and +6, each 6 units away from the origin. The origin is going to be the center of our ellipse. And so if I sort of take that string and I draw it taut, I can create an ellipse. And that ellipse, each point on that ellipse, if we take the distance from any point on there, the distance from this point to this focus plus the distance from this point to the other focus is constant, that distance being the length of the string, right? The string is not. So, and then also we could bring it over here and complete it. We could do the bottom half of it if you want it. Something like that. Okay? So that is how we can create an ellipse. So now let's look at it a little bit more closely. How does the shape of the ellipse change? We're going to keep the same string length. So the distance between the foci from a point to each of the foci summed up is going to be constant. What happens if I take, well, let's do this one first. Let's do the foci that are closer in. And I draw an ellipse. What is going to change about its shape? All right, so let's try that. Start over here. So let's start over here. So you can see it's going to have the same sort of endpoint down here, which makes sense because that string length is going to be the same, right? From this focus out here and back again should be consistent because it's the same string. But what happens on the other side, on the minor axis? You can see that now we are getting what you might think of as a little bit more rounder ellipse, less elongated. Let's continue it down here. And you can see here that it is indeed less stretched out, more sort of circular. Okay, the closer the foci are together. So you could kind of surmise what would happen if the 2 foci were right together, right on the origin. And so you could probably think about that a little bit and realize that it will probably be super circular or actually a circle. All right, now let's try it with, now my knot is sort of in the way a little bit here, but let's see what we can do. Now let's do it with the 2 foci that are even further away from each other. You can see now it's even more sort of elongated, stretched out, skinnier. Let's do the other half of it while we're at it. My knot's sort of in the way there, so it's not going to be perfect, but you can kind of get the idea. So the further away the foci, the more sort of elongated and stretched the ellipse becomes. And then the closer the foci are together, the more circular looking kind of it is. All right. But again, this distance, let's use these, the distance from a focus to a point on the ellipse plus the distance from that point to the other one is the same. So if you kind of think about this point right here, we're going to call this distance C, the distance from the center of the ellipse out to a focus. That's going to be considered C. The length of the major axis, that's going to be referred to as A. And then the length of the minor axis is going to be B. But if we look at like this right triangle right here, okay, well, we know this one side is C and this one side is B. Interestingly enough, that distance along here, the hypotenuse, that's going to be equal to A. If you can see, well, I can kind of show this really easily if I take my string. So that string length is the same as the length of our major axis. So this string is 2A, okay? We refer to, from the center to the end point of the major axis is A, so this whole length is 2A. That happens to be exactly the string length, right? So now, if we think about putting these back on the foci, half of that string's over here, half that string's over here, so that distance is A. So it's not like we're turning the Pythagorean theorem on its end, but here we know that we're going to have that B squared plus C squared is equal to A squared. Not that the Pythagorean theorem is now wrong and we've changed it. It's just what we call the hypotenuse now. In these cases, it's more convenient to call that A because it happens to be the length of the half of the length of the major axis, which is 2A. So we're going to use the formula B squared plus C squared equals A squared. It's still the Pythagorean theorem. The two legs, which we happen to call B and C, each of those get squared, added up, and it's equal to the hypotenuse, in this case, A squared. So now let's get to our notes. So we're talking about notes 10.2, which is ellipses. You've already looked at the YouTube video about Kepler. That was pretty interesting. And I've discussed already the sort of the definition of an ellipse and how we can use that to create an ellipse. The sum of the distances between a focus and a point, and the point and the other focus is constant. We saw that in the string that we were just using. And we can think about that. This is a diagram from a book published in 1670s that talks about an elliptical ceiling. And so if we think about two people standing at the foci of this ceiling, which is elliptical, and this person, let's say at point A, out here at A, is talking, the sound waves coming out of his mouth are all traveling in all directions, and they're hitting the ceiling, and then they're bouncing directly to this other focus, point B. And even though this person at point A is maybe talking very quietly, all of the sound waves that are hitting that ceiling are bouncing off and arriving at point B, the other focus, at exactly the same time, because those distances, the distance from A to the ceiling to B, no matter what path you take, are all the same, because that's what the definition of an ellipse says. And so you could be standing here with your ear at point B and hear everything that this person's saying, even though they're talking very quietly on the other side of the room. So there's lots of old buildings that have elliptical ceilings where this kinds of thing happens. All right, let's get to some of the terms now. The first thing we want to do is draw in our major axis. The major axis is the axis, sometimes we'll draw it beyond, but the major axis is from this endpoint to this endpoint, and it's referred to as 2A. The minor axis is perpendicular to it, and that is referred to as 2B. So we think about this length, let's do it here, this length here being A, and we call this length up here B. And now there are two foci here, And I'm just going to draw them in. They're a little more than 6 away from the origin, from the center. 1, 2, 3, 4, 5, 6. Now, you don't get to pick where those go. They are determined by the eccentricity of the ellipse. 1, 2, 3, 4, 5, 6. A little bit more than that, I think. Wait a minute. 1, 2, 3, 4, 5, 6. Did I draw this one in the right spot? 1, 2, 3, 4, 5. Nope. I think it's a little bit beyond that. So draw yours in a little bit beyond 6. Now, the further away those foci, the plural of focus is foci, so the further away those foci are, the more stretched out or eccentric the ellipse will be. The closer they are in the center, the more circular, more closer to a circle that the ellipse will be. All right, so universally, the distance from a focus to the center is just referred to as C. You're going to see that in some other conic sections as well. And then in the video we just saw, we saw that this length here, which was half of our string length, right, or half of the major axis, or that's A. All right, so we now have a relationship between the A, the B, and the C for every ellipse, and that relationship is that the half the minor axis squared plus the distance from the center to the focus squared is equal to half the major axis squared. All right, and so that's not to say that somehow the Pythagorean theorem doesn't work anymore, like, oh, it used to be a squared plus b squared equals c squared. It's just for ellipses, it's convenient to call the distance from the center to the focus c, and we do that for other conic sections that have foci as well. And so for hyperbolas, which we'll get to later. So it makes sense just to be consistent, even though this is inconsistent with the Pythagorean theorem and how we usually look at right triangles, it'll be consistent for the conic section. So that's why we sort of do that. All right, so again, this is the, we call this the major axis. And then this one here is referred to as the minor axis. Okay, the minor axis being the longer one that the foci are on, and the minor axis is the shorter one that the foci are not on. Okay. All right, so let's look at some general formula for an ellipse. So these are simple ones where the center of the ellipse is at the origin, 0, 0, and then we'll get to more complicated ones on the back of the first page here, on page 2. Again, the distance from the center to the focus is C, the minor axis, half of that is B, and the length of the major is referred to as 2A, so this distance will be A. All right, so if the major axis is horizontal, then the bigger of the two, A, B, A is always the bigger, right? The bigger is under the x squared. The minor axis, B, or half of the minor axis, is under the y squared. So A squared and B squared. The foci are located at plus or minus C, comma 0. Again, length of the major axis is 2A, length of the minor axis 2B. All right. And so that still applies, those still apply down here. The length of the major axis is still 2A. The length of the minor axis is still 2B. The foci now, if it's vertical, are at 0 plus or minus C. Okay. Notice too that the bigger of the two numbers, A squared, is now under the y squared rather than being under the x squared. And that, again, is when the major axis is vertical. Okay, let's do some examples then. Number 1. All right, so we want to graph this thing. So first, we want to probably put it into one of these forms, right? So we want this 144 to be 1. And so I guess we could subtract 143 from both sides, but you can probably see that that wouldn't work. So probably the better thing to do is to divide through by 144. Okay, and so both of these are nice. They reduce to a nice fraction. So this ends up being x squared divided by 9 plus y squared divided by 36, and that's equal to 1. And so now let's think about, is this going to be an ellipse with the major axis vertical or horizontal? Okay, so the bigger number, which is always our a squared, is, of course, under the y, so that means this is going to be vertical. So it'd be helpful to write down what a is equal to. So a is equal to 6, because 36 is a squared. B is equal to 3, and find C. So C squared is going to be the difference of these two, which is 27. And so C is the square root of 27. And so, yeah, I mean, you know, we would want to simplify that. We could say that is, what, 3 square roots of 3. But this doesn't really make it any easier to graph. What we want to think about is, what's that approximately equal to? It's easier to think about square root of 27 to think about what's this approximately equal to. And we know the square root of 27 is a little more than 5. So this will be equal to something like 5.2 or so. All right, so we want to graph this. So we know this is centered at the origin, so I can just simply put in my xy axis right in the middle here. All right, and so my A, again, is going to be going vertical. So I'm going to go up 6, 1, 2, 3, 4, 5, 6, and down 6, 1, 2, 3, 4, 5, 6. Find the endpoints of the minor axis. That would be here at 3 away and 3 away. And now the foci, you know, something here. So this is a fairly eccentric ellipse because the foci are pretty close to the endpoints. And now sketching this. So this is kind of hard. It's going to take some time to get used to sketching these. But try, you know, it's going to be sort of flat at each of the endpoints of the minor and major axis. Try not to make it look like a football. Try not to make it look like a rock. Okay, something like that. All right, now let's look at number 2 then. Write the equation for the following ellipse. All right, so they tell us where the foci are, and they tell us the length of the major axis. So find A, B, and C. And then once you know those things, you should be able to write the equation based on whether it's vertical or horizontal. All right, so we know this one is centered at 0 because we can tell, like, where's the midpoint between these two values, and so that would be 0, 0. Also, the only things we're doing right now are centered at 0. They're going to get more complicated in a second, but for now, that's as complicated as they get. All right, so so this tells us that C is equal to what? Yep, 4. And then what does this tell us? This tells us that it's the major axis, so that means 2a is 14, a equals 7. All right, so now using these, we should be able to find our b. So we know that a squared minus c squared should equal b squared, right? Using our formula from up above. And so that would be what? 49 minus 16 equals b squared. So that's 33. B squared equals 33. And so if we wanted to know what b was, well, that would be the square root of 33. But our formulas require us to use b squared anyway, so we don't really need to write what the square root is. If we could simplify that, we wouldn't even bother with it because we want b squared in our formula. All right, so is this oriented vertically or horizontally, right? Is the major axis horizontal or vertical? Remember that the foci are always on the major axis. So we need to determine, are these foci next to each other or are they above each other? And so we can see the y's are the same. So that would be a situation like this where they would be next to each other. So that means our formula is going to be x squared over the a squared, because that's, again, the bigger number, so 49, plus y squared over b squared, which was 33, equals 1. All right, let's continue on page 2 of the same notes, section 10.2, ellipses. Okay, so now we're dealing with more generalized formulas for ellipses that are centered at some other point other than the origin. So HK is going to be our center. And so if you remember back when we did circles, this kind of looks a lot like the equation of a circle, right? We had x minus h quantity squared plus y minus k quantity squared is equal to r squared. So here we don't have one r. It's almost like we have two radii. We have a large radius and a small radius. So it's very similar to the equation of a circle. Now here, a squared, the bigger number is under the x. So the major axis is horizontal. And so it's the center, h comma k, and the c value is added and subtracted to the h. So here's hk here. And so it's plus c and minus c to the h. So that would give us our location of the foci. So for the vertical, again, the a squared is under the y. And also we're adding and subtracting c to the k value. So here's hk. This is h comma k plus c and h comma k minus c. So we're adding and subtracting c to the k values when it's vertical. All right, so let's look at some examples then. Example 3. Okay, so they give us an equation. We really want to put this equation into one of these forms up here. This one's still pretty easy because you can see, since there's no x or y, separate x and y terms, we know this one is still centered at the origin. So this one's pretty easy. If we divide through by 2,916, both of these are multiples of that. And so we get something like x squared over 81 plus y squared over 36 equals 1. And so we know our a squared, we know our b squared. C squared would simply be the difference of those two. And so c is going to be equal to the square root of 45. And again, you could simplify that. If I wanted an exact location, I would probably want that in radical form. So we would say, what? A 9 comes out of that, so 3 square roots of 5. But for graphing purposes, we want to think of it as the square root of 49. We know that's a little less than 7. I'm going to call it 6.7. So for graphing purposes, so we know. All right, so now, which way is this thing oriented? This thing is oriented horizontally because the a squared is under the x. And since it's centered at the origin, let's just go ahead and put our axis right there in the middle, our x and y axis. And let's see, where's the center? About there, I guess. Now, my a is 9, and I'm not going to be able to fit that, so I'm going to change my scale to 2, both on the x and the y. If you change your scale, I would say change it in both directions, x and y. So that's a 2, and that's a 2. Okay, and so now when I count over from major axis, I'm going to count over 9. So that's 1, 2, 3, 4 and a half on my scale. And so 1, 2, 3, 4 and a half, which is 9. Those are the endpoints of the major axis. Now the minor axis, I'm going to go up 1, 2, 3, which is really 6, and down 3, which is 6. Okay. Now I could sketch that in without really putting in the foci. Again, try not to cut the corners too much. Sometimes when people draw this, they tend to go more straight across here as though they're cutting the corners, so don't do that. And again, just practice will make this easier to do. you've never really had to draw an ellipse before, so it can be a little tricky. All right, and then let's go ahead and put in the foci. So that's 6, like 6.5. So that's what, 1, 2, 3, 4, 5, 6. That would be 7. So you know, about 3 1/4 on our scale. So about 3 1/4 or so, something 3 1/3, something like that. So those are the location of the foci. Often when we ask you to graph these things, we'll want you to put in the foci as well. All right, try number 4 then. This one's a little bit trickier. We have x and y terms, so we know this thing is not going to be centered at the origin anymore. So pause the video and try to put this into that term, and then you can restart the video and see how to do it. All right, so yeah, I may not have given you a whole lot of space here. You might have to write pretty small. Hopefully you did. So I'm going to put the x terms together. We have x squared minus 4x, and then I'm going to leave a space, and then we have plus, and then I'm going to factor the 9 out of this y. Because remember, what we're going to end up doing is completing the square for the x and completing the square for the y. It seems a lot like what we did when we were doing this for circles. All right, so I'm going to factor the 9 out. I got to factor the 9 out of the 50, so it's y squared, and then take the 9 out of the 54y. So that gives us 6y, and then leave a space. And then I'm going to move the 49 to the other side. So that's negative 49. All right, so what goes in here to complete this square? I have to add a 4. So I do that same thing. I add a 4 on this side. And then what goes here? It's half of this 6, half of that 6, which is 3, squared, which is 9. Now, we're careful, I'm not going to add a 9 over here. I'm going to add that 9 times 9. So when I added that 9, its true value was 9 times that, or 81. So I added 81 to one side. I'm going to add 81 to the other side as well. So I've got to add a 4 and an 81 to the right-hand side. All right, so I think I can now write this. This is going to be x minus 2, quantity squared, plus a 9, times the quantity y plus 3, quantity squared, equals, and this ends up being 36. All right, now this looks a lot like the equation of a circle, except for now what we want to do is we don't want the number over here by itself. We want this to be a 1. So I'm going to divide through by 36. So I get, finally, I get x minus 2 quantity squared divided by 36 plus, and then what does this become? Y plus 3 quantity squared over 4. So you think of it as 9 over 36 and reduce that fraction to 1 over 4. All right, and that gives us a 1. So clearly now our A is 6, our B is 2. What would our C be? So C is the difference, C squared is the difference of these two, so that would be 32. So C is the square root, 32. Of course, we would like to think of that as, we might want to simplify that as a radical, and so we would pull a 16 out of that. So 4 square roots of 2, or we would want to, for graphing purposes, try to approximate what that is. Well, 36 is perfect square, so that would be 6. So this is a little less than that. You'll find that this is about 5.7. Okay? All right, and so now let's graph this thing. Think about how it's oriented. All right, the bigger number is on the under the x, so we know this one is horizontal. I'm going to go ahead and put the center right in the center. Okay, and so what would be the center? Actually, let's find what that coordinate is. So the center, center is where? So that's going to be 2, negative 3. So to make that point 2, negative 3, my y-axis has to be here. And for this to be negative 3, I need to go up 1, 2, 3. I need to put my x-axis here. So that makes that point 2, -3. All right, and so from that center, I go plus or minus 6 away in the horizontal direction. 1, 2, 3, 4, 5, 6. All right, that just fits if you put that right in the center. 1, 2, 3, 4, 5, 6. So those are the endpoints of the major axis. And then this one is really eccentric. So the foci are really close out here, right? So they're about there and there. They're pretty close to the endpoints. And so let's try to sketch this one in. We don't expect your ellipses to be perfect, certainly not at the beginning of this, but something like that looks good. Okay? All right, let's move on to number 5. All right, so this time write the equation of the ellipse. So we want to write it in one of these two forms. So the endpoints of the major axis are here, and the foci are here. All right, so it doesn't say specifically to graph it, but you might find it helpful, but you should just think about, okay, are these 2 points, the major axis, are they next to each other or above each other? And you notice they have the same y, so as a result, these would be next to each other. And so also, the distance between these is equal to 2a, and so what is the distance between those? The distance between them would be 18. That's equal to 2a, so a is equal to 9. Okay, so that's one value we're going to need. All right, let's find the center. How could we find the center from these two? All right, so the center is going to be the same height as those, so I know it's 2. And so it's the midpoint between those. These are the endpoints of the major axis. The midpoint of that segment will be our center. And so that's going to be a 1. You could also find it using the foci, because what's dead center between the foci? The center. All right, notice these are also on the same major axis, right? They're at the same height too. These, though, the reason we need these is to give us our C value. So remember, the distance between those 2 points is 2c, so I think you can see that that's going to be 10, so C will be 5. So we need that value as well. We don't find that C finds its way into the formula per se, but we need C and A in order to find B. Okay, so so if we do 81, right, A squared minus 25, C squared, that should be equal to B squared. And I think you'll see that B squared is 56, so B is equal to the square root of 56. But ultimately, we don't need to think about simplifying that, because what do we need in the formula? We really want B squared. So B squared is 56. That's all we really need. All right, and so how is this oriented? All right, we talked about how these are next to each other. So this is definitely horizontal. And so now we can write the formula. We know this is the general form. We just need to figure out what values go underneath there. Since it's horizontal, we want A squared, the bigger one, under the x. So 81, and then 56. Okay, and if you felt like you wanted to graph some of these things to help you visualize them, you could certainly do that. All right, example 6, write the equation of this ellipse. Why don't you pause the video, try this on your own, and then turn on the video and I will work through it. Okay, I think you can see that these two endpoints of the major axis are vertically above each other. They have the same x coordinate. So this one is definitely vertical. And the distance between these is certainly 2a. And so the distance between these is 16. So that's equal to 16. So that means A is 8. This time they didn't give us c, they gave us a way to find the length of the minor axis, which is 2b. And so the distance between these 2 points is 4, so 2b is 4, so that means b will equal 2. All right, so now again we have x squared over something plus y, nope, I goofed on these, sorry. This one I did not put the center into the equation. Let's go back and fix that, sorry. I was thinking we were centered at the origin still. All right, so this is x minus something squared and y minus something squared. We'll go back and fix that too, because this is not centered at the origin, so we're going to have things next to the x and next to the y. All right, so we have x, did we find the center? Yeah, here, x minus 1 and y minus 2 quantity squared is what you want to do based on the center. Remember, it's always, when you're pulling it out of a parentheses, it's always the opposite. So x minus h, y minus k. Okay, so now do it down here. All right, so this is x minus, okay, did we find the center? So we need to figure out where the center is here. So we know that the center definitely has an x coordinate of 2 because that's where the two endpoints of the major axis are. And then so we just need to think about the midpoint between those. And so I think if you do a little math, you see that that center is at 4, right? We add those up and divide by 2, gives us the midpoint. All right, so now we have x minus 2 quantity squared over something plus, and then y minus 4 quantity squared over something equals 1. And so now we just got to figure out what these are. Again, this time we're going to put the a squared under the y because this is vertical. So that is what, 64. This one, 2 squared, which is 4. Okay. All right, this time they actually drew us an ellipse, including the location of the foci. If they draw the foci right at a corner, you can assume that you know exactly where it is. But if it's somewhere in between, you cannot guess. You have to be given some kind of information to be able to figure that out. Like for example, we don't know what B is here. Right, we can't tell how long the minor axis is. The endpoint of the major goes through an actual point, so we can count the 2a, but we can't really count what 2b is. We have to use c in order to do that. All right. So first, let's to write the equation. So first of all, try writing the equation. Pause the video, and then turn it back on and to reveal the answer. All right, so we first need to find what the center is, because in order to find the equation, what do we need? We need h, we need k, so we need h, we need k, we need a, we need b. And we need to know the orientation, how it's oriented. So we need those kind of 5 things to be able to get this. So know the orientation, it's vertical, right? But we need to find the a value and the b value, and we need to find the center. Right? All right, so this one's done. We know the orientation. We just need to find these other 4 things. So first, let's find the center. So we want to go halfway between these. Let's count. From this focus to the other one. 1, 2, 3, 4, 5, 6, 7, 8, 9. So half of that's 4.5. So we do 1, 2, 3, 4.5. So the center is here. I'm going to draw my minor axis in. And then I can also draw my major axis as well. All right, so that was 9. So I know 2a is 11. And I don't know what 2b is, right? Because I can't tell. But I can tell, what I have to do is be able to use a and c to find my b. So I know that 2c is 9, because we just counted that. So that means a is 11 halves, C is 9 halves. Okay, so what we want to do is find B. So I know that B squared is equal to 11 halves squared minus minus 9/2 squared. Okay? So that ends up being 121/4 minus 81/4. Actually, that works out pretty nicely. That ends up being 40/4, which is 10. So that one actually ends up being kind of nice. The other ones are a little messy. So b squared is 10, and again, we're writing the equation, so don't worry about trying to find the square root of 10. For b, we just need b squared. So I think we're ready to write the equation. Oh, we need to find the center too, right? H and K. So we know the H, let's see, we go over 1, 2, 3, 4, 5. So the center is at, I don't want to use C because C means something else here. So center, let's write it out. Center is 5, comma, and then let's count up how many we have to go. We have 1, 2, 3, 4, 5, 6 and a half. So, I mean, we could say 6.5, or we could do 13/2, either one, right? Okay, so now we have the center, we have H, we have K, we found our A, right? We know A, we know B, well, B squared, which is really what we want. And so let's write the equation. So it's going to be x minus 5, quantity squared, plus, and then y minus 13/2, quantity squared, and that's equal to 1. And then which one of these goes here? So remember, the a squared is going under the y because it's vertical. And so that's, you know, here's a, we need a squared, so 121/4. And then this will be 10. Now, technically this is not simplified because this is a fraction within a fraction. So we could get rid of this 4 and put it up here. Sometimes you'll see that, but in this case we sort of want it to be non-simplified because we want this denominator, fraction or not, we want that to be down here so that we know what a squared is. We put the 4 up there, we're tempted to think about our a squared as being 121. Okay, so here is your homework. Work on that, and then we'll work on the 3rd page of these notes on our next class.